All right. First off, no, you don't.
Yes,
You have an effect on it. You don't control it. You cannot make sense out of the statement being both true and false at the same time. Doesn't matter how hard you try. To say you can is to have an
no,
equivocal definition of
you
sense.
make everything that makes sense to you make sense to you.
You have to make it sense. It doesn't make sense unless you make it make sense.
Yeah.
But you don't have a choice of what is going to or not going to make sense. You can make things that do make sense,
Yeah.
make sense to you. That's it.
Yeah, that's what I'm saying.
You don't have control,
You have control over
over
what
makes sense to you.
Yes, you do.
You have a control of the things that you're going to go make sense of that already make sense.
So what that makes sense to you.
Okay.
Exactly.
If that's the way
You're
you mean it,
right.
then okay.
Okay.
You're using confusing language, if that's what you mean.
It's just English, it's not hard.
Let's see. Groups. Okay, so where are we starting today? Today we are starting algebraic structures. First off, don't let me go past this line without moving the camera. Okay. Or you'll miss like the only major proof we're doing today. So today we're starting the chapter called Algebra. This isn't algebra, well, it is algebra like you've been doing algebra, but algebra like you've been doing algebra is studying very specific structures over and over again. We're going to do a more generic study of algebraic structures. The simplest algebraic structure, the one that we're going to start out talking about today, is called a group. A group is a very simple algebraic structure, and it's a mathematical structure the same way that different structures that you've already worked with are structures. For example, we've talked about a sample space. You remember what a sample space was? What was it? SP, what was S?
Everything inside.
It was just some set, some non-empty set, and I think it's also fine. And then P was the probability function. So P gave some sort of structure to S. So S was just some set, and P gave it some sort of structure. For those of you doing topology, we do the exact same thing. What's a topological space? We have some set, and then we have its topology, which gives it structure. We're going to be doing the exact same thing here again. We're going to be talking about some set, G, and we're going to be giving it some structure, just a function. In this case, a function's a dot. Just like you had SP, we're going to have G, and then some other function that we're representing with a dot. That's what a group is going to be. It's going to be that structure. So that's often what we do in different maths is when we're talking about a structure, we talk about a set, and then some sort of something else that gives structure to the set. Like a probability function, or in this case, we're going to talk about a certain operation, or in topology, we talk about a topology, obviously. We just did metric spaces. Metric spaces, you take a set and a metric function.
Yeah.
And that gives you some sort of structure. So group is just like that. That's what we mean by it's one of the simplest algebraic structures we can talk about. So that's kind of high level what we'll be doing. We'll get to a bunch of definitions before we actually go over exactly what a group is. So first definition. Let A be a set. An operator on A is a function whose domain is A cross A. What's an operator on A? It's a function that eats up two A's. Two elements out of A. Let's do an example. So let's say we've got f from z cross z to z by f of ab equals the absolute value of their difference. Now you guys know that that gives us the what? The distance. That gives us the distance on the number line between two integers, right? So here's our operation. You give it two integers and it spits out one integer, right?
Yeah.
Notice its domain is two integers. In this case, it's a and b. So, for example, f, if we give it 3 and negative 2, it spits out 5. The distance between 3 and negative 2 is 5. Here's an example of an operation on the set of integers. Because its domain is z cross z. Operation, just a function. An operation on set A is a function whose domain is a cross A. So an operation on z is a function whose domain is z cross z. That's all it is. Feel like you got that? Yeah, pretty simple? Okay, so let's look at some other examples. Let's look at plus, minus, times, divide on the natural numbers. I want you to tell me which of these are operations and which ones aren't. Plus on the natural numbers. Is that an operation?
Yes.
Is it?
Yeah.
Okay, what about subtraction?
Yeah.
Yes.
No.
Because you can do like 2 minus 5, right? And that gives you a negative number, which isn't natural.
I'm just confused.
You know what plus is.
Yeah.
You know what the naturals are. Can I add 2 naturals?
Yeah.
Can I add any 2 naturals? Yeah. So plus is an operation on the naturals. What's an operation? Let A be a set. An operation A is a function. An operation on A is a function whose domain is A cross A.
Oh.
Plus on N.
Yes.
Is that an operation?
Yeah. So you're saying n plus n? Just any number in n.
Plus, where you're adding together elements of N. Plus, where plus, let's write out plus explicitly. Maybe you're not used to thinking this way. Plus, where it's a function from N cross N to N by, well, we can't define it because we need plus to define it.
So you're saying even if the operation happens, then I'll still be n? Yes,
In
it'll
n.
still be n. Okay.
Plus can take 2 natural numbers and spit out natural numbers.
Okay.
That's what plus does. So when I apply plus to 2 and 5, it spits out 7. Right?
Yeah.
Nothing weird?
Yeah.
I mean, I know that's weird notation for you to see with plus, but plus is just a function and it's a perfectly valid notation. We just rarely use it.
I have a question. So you say there's an operation on A. Does its image have to be A?
Now, look at the definition. It says nothing about the image,
Oh,
That's
just the
right.
domain.
So minus does work then.
So let's wrap our heads around plus first. Plus is plus on N an operation on N?
Yes.
Yes. I can take plus and have its domain be N cross N. Subtraction.
Yeah.
Yes? No?
Yes,
Yeah.
but how?
Yes. Can I subtract any 2 natural numbers from each other?
Yeah.
Mm-hmm.
So subtraction on N is a function whose domain is N cross N.
How does it come out as n though?
I never said it comes out as N.
Okay, but then it's not.
Well, we didn't say, look, subtraction we can define on the naturals by N cross N to Z. It will always be out an integer, not necessarily a natural, right?
Then you can do any of them.
Well, we'll work it out one at a time. Don't jump ahead. But make sure that this makes sense. I can have this function with this as its domain, right?
Mm-hmm.
So we're good? Doesn't matter that the codomain or the image isn't the naturals. This says nothing about the codomain. It just says let A be a set and operation on A is a function whose domain is A cross A.
What does that mean? The domain is a.
The domain, this part, what it's mapping from. All the left-hand elements of the function.
Yeah, well, okay.
Alright, let's go to times now. Can times be an operation on N?
Yeah.
Yeah? I can take any 2 natural numbers and multiply them together?
Yeah.
Oh, crazy. And then what about divide? Can that be an operation on N?
No.
No. No?
Why?
Why?
Yes, you can't divide n.
Because you can't divide by 0. So the domain is not all of N cross N,
Oh.
right?
You just get 0, but that's still a number.
3 divided by 0 is 0. Use your, it's what?
It's 3.
It's 3. 0 goes into 3 times.
Oh, it's.
Take 3 zeros and you got 3. No, that's 1. Take 3 ones and you got 3.
It's 0.
How many zeros do you got if you take 3 zeros?
0.
0.
Exactly, so it's 0. So you can, it's just 0.
So now think about it this way. You're saying that 3 divided by 0 should be 0, right?
Mm-hmm.
Well, what about 3 divided by 0.0001? Let's calculate this. This is 3 divided by something that's almost 0, right?
No, it's just 1.
That is a very small number. Do I need my leading decimal?
Okay.
That is a very small number. Are you reading the number from right to left? This is English. Left to right. Okay. So you're good with this, right? Now what does this equal? If that's hurting your brain, you can think about it this way if you want. 0.0001 is the same thing as 1 over 1 0, 2 zeros, 3 zeros, 4 zeros. Trying to slowly show you how you've been taught to think about it. We're doing 3 divided by 1/10,000.
Okay.
Or 3 divided by 1/10,000, right? When you divide by fractions, you multiply by the reciprocal. This gives you 30,000. So 3 divided by 1 is equal to 3. 3 divided by 0.1 is equal to 30. 3 divided by 0.00000001 gives you 30,000. But if you do 3 divided by all the way to 0, you just get 0. So as we get closer and closer to 0, we get bigger and bigger numbers until we get to 0, then it's 0. Right?
Yes.
Your brain's not already screaming up that trunk?
Yes, I understand that.
Okay. Another way to think about it is division is a reciprocal of multiplication.
So 3 divided by 0 is then fine.
Yes.
I feel like I've never learned that.
Not only have you learned that, we have gone over that specific thing in this class. And we had a whole conversation about it. So I don't think you've ever paid attention to that.
Okay.
That's probably a better way to say it. Alright, so we've got that division is not an operation on n cross n. But the other ones are all on n. So this can be an operation on n, this can, nope, not this one. We can make this one an operation on n. We just need to restrict its domain, so it's not really an operation on n, we make an operation on the naturals minus 0. And then we can do that across itself and make that its domain. Restrict the domain. And I guess you guys didn't do trig yet,
Okay, you just do R1.
but it's a common thing that you do in trig is restrict the value of a function. What they call trig. Maybe it's actually in college algebra and I'm just thinking of the hybrid version. But restricting domains of functions is a common thing that you've done to find out where they behave nicely. So division is defined everywhere except for when we try to divide by 0. That's the one case that we can't do. Good? Basic operations that you know and love. And then wanted to make sure that you know that even though this is typically how we write, plugging two things into a function, when our function is an operator, we tend to write it this way, where we put the function symbol between the numbers rather than writing it like this. Make sense? Okay. But still just a function. Still just a function that takes two things and spits out one thing. Just a function. Okay. Now, from here on out, when we're talking about a generic operation, so the same way that when you were in your first algebra class and you came across a letter X and you're like, how am I going to do math with numbers or with letters? What is X? And they try to click in your head, it's a variable. It's any number. Right? Similarly, we're now going to be talking about the operation dot. What operation is it? Any operation. It could be function composition, it could be addition, it could be multiplication. It doesn't matter. It's just an operation. So from here on out, we'll be using this dot symbol. This is not times. This is not multiply. For the rest of this, every time I use that dot, it's just a generic operation. The author uses star for his generic operation, but it's very common when you're studying the field is called abstract algebra. Most times you study abstract algebra, the symbol that's going to be used is just a dot for a generic operation. Okay, so from here on out, you'll see the dot. It's just an operation, and it is not multiplication. Good? Mm-hmm. All right. So let dot be an operator on A. We say that dot is commutative, provided that A dot B is equal to B dot A. We've talked about commutative operators 100 times in this class. Now we're just stating it in general. We say that dot is associative, provided that A dot B dot C is the same thing as A dot B dot C. Associativity. You're used to that property, right? And then here's one that might be new. I don't know if we talked about this before or not. We said the operation is closed if for any two elements in A you pick, A dot B is also in A. That means the operation is closed. So coming back up here, addition is closed on the natural numbers because if you add two natural numbers together, you get a natural. Subtraction is not closed on the natural numbers because if I do 1 minus 100, I get a negative number, which is not a natural, it's an integer. So addition is closed on the natural numbers, subtraction is not closed on the natural numbers, multiplication is closed on the natural numbers.
So it's if the image is filling.
Sorry, say that again?
So it's if the image is filling?
Yes. Or a subset of. Okay. So that was closed. So any question about these three properties, commutative, associative, and closed? Feel like you understand what it means for an operator to have one of those? Okay. Next definition. Let star be an operator on a set A, then little e in A is called an identity element for dot, provided that for all little a and big A dot E is equal to E dot A is equal to A. If E satisfies this, we call E an identity element. 1 is an identity element for multiplication because A times 1 is equal to 1 times A is equal to A. 0 is an identity element for addition because A plus 0 is equal to 0 plus A is equal to A. Does that make sense?
Yeah.
So depending on what set you're talking about, what operation you're talking about, you can have a different identity element. If we're talking about function composition, or if you remember back to talking about permutations, you remember talking about permutations, those functions, and we talked about the identity permutation, we used a little iota symbol for it. That operated as the identity element for composition, for permutations. You remember this thing, S sub n? You remember that set? The set of all the permutations that you can make on an n element set, the numbers 1, 2, 3, 4, 5 up to n. This was the set of all the permutations, all the one-to-one and onto functions, bijections from n to n. Good? And we used symbols like this to represent permutations. So, we talked about how every permutation has the iota function, the identity function, which just maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, all the way up, all the way to n to n. So, iota sigma pi, for any permutation pi, is equal to pi I just lost the name. What is that? Composed, thank you. The same thing as pi composed with iota, no dot, is the same thing as just pi. And that's one of the things we did quarterback when we were talking about permutations, one of the first.
Right.
And it turns out SM with composition is an example of a group. It's not a coincidence that all these things have these properties. So there's another example. So we don't always have to be talking about plus and multiplication. Let's go to another one. Let's say that we're talking about Boolean values. What do we call them in this class?
Sure is Boolean values.
Oh, you know, okay, I thought that was a computer science term. Everyone here knows what I mean by Boolean? True or false?
Yes. Oh, yeah.
Okay, so we're on the set, there's just true and false, right? So there's our set. And now we need to give it an operator. What's an operator that works in logic? And, so we can take that set with the AND operator, put that together, turns out that's going to be a group. Now what's the identity element? I need to find something such that x and that something, we need to fill in the blank, is equal to that something and x is equal to x. True. True is the identity element when we're talking about AND. Look, if x is true, then this whole thing's true.
Oh, okay.
If x is false, this whole thing is false. X is a Boolean variable, which means it can only be true or false. Does that make sense? So all we can do is plug in true or false for X. If you plug in true for X, this is true, this is true, this is true. You get X. This is the same thing as X. If you plug in false, this is false, this is false, this is false. So if you're looking at the set of Booleans and the AND operator, your identity element is true. What about if we switch this to an OR?
It's false.
Then our identity element is now false. Make sense?
Yeah.
So there's another example talking about some other set, some other operation, and its identity elements. Good? Okay. So hopefully that helps us realize that we're talking about things more abstract and we're not just talking about class and multiplication. So now super. Let dot be an operation on some set A, and let E, we will always use E for identity element from here on out. I might accidentally forget to specify that E is an identity element. From here on out, you see a little E, it's always and forever an identity element. Good? So, let dot be an operation on A, and let E be an identity element for dot. Then E is unique. What are we saying? We're saying that if an operation has an identity element, it has one and only one identity element. That's what we're going to prove. Assume by way of contradiction that there exists two identity elements in A, such that they're both identity elements and they're not the same identity element. It's going to lead to a contradiction. Well, then E is equal to E composed with E prime, right? Because E prime is an identity element, so anything composed with E prime gives you back that thing. But since E is an identity element, then E composed with anything gives you back that thing. So E equals E prime. Contradiction. Very simple. The exact same thing we did in logic.
Yeah.
So contradiction, therefore there's at most one identity element. Good? No questions? Next?
Yep.
Alright, let dot be an operation on A, and assume A has an identity element E. Then B is an inverse of A, provided that A times B is equal to B times A is equal to E. That's almost exactly how we defined an inverse element when we were talking about modular arithmetic. What was, so pretend that we're in Z10 for a second. And what was the multiplicative inverse of 3? 7. How did you get that?
Because when you go 3 times 7 is 21, 4 divided by 10 is 3.
Because 3 modulo times 7 equals 1. So 3 times 3 inverse is the same thing as 3 times 7, which is equal to 1. The point is, the way that we defined 3 inverse was the magical number such that when you multiply by 3, you get the identity element. That's what inverse is. It's also how we go about defining inverses if we're talking about addition. What's the additive inverse of 3? It's negative 3. Negative 3 is a magic number such that when you add it with 3, you get the additive identity, namely 0.
Okay.
Back to just regular algebra, like you know and love. What does 3 inverse mean?
1/3.
It means 1/3. And notice that 1/3 is the one and only one number such that when you multiply by 3, you get 1 in regular algebra. So 3 inverse times 3 is the same thing as 1/3 times 3, gives you back 1. Same thing. So this is an inverse of this with multiplication. Just like negative 3 was the inverse of 3 on addition. Make sense? Yeah. Okay, so back to this. Make sure that this definition makes perfect sense. B is an inverse of A, provided that A dot B is equal to B dot A is equal to the identity element. Does that make sense?
So either way is equal to that.
Yeah, it doesn't matter what order you do it in. For a group, it turns out if you have it just one way, you can prove it the other way. That's what we did in logic. We're going to start with more structure on a group here than what we started with in logic. And in in logic we worked our way up to showing that if this is equal to E, this is also equal to E type stuff. So you could end up getting there even if you started with a little bit weaker structure. Okay, so now let's look at a really strange example. Consider dot on the set E, A, B, C by, here's the operation. If you give it an E and an E, it spits out E. This is just like a times table, right? You remember your times tables, you wrote your numbers across the top and the bottom, and you multiply them together and fill out the square?
Yeah.
We're doing the same thing. Except for we're doing the dot table now instead of the times table. Good? Okay, so we're defining this operation right here. Notice E is an identity element. E dot E gives you E, A dot E gives you A, B dot E gives you B, C dot E gives you C. Similarly, E dot E gives you E, A dot E gives you A, B dot E gives you B, and C dot E gives you C. So it's an identity element. If you dot with E, it just gives you back whatever you dotted it with. Whether you do the E first or the E second, it's all the same. We'll say that we're dotting this with this. Good so far? And that would just fill out the table the rest of the way. It's somewhat arbitrary. And if you look at this and try to find some reason pattern, you're probably not going to find one. We just made sure that that was an identity element and then kept it symmetrical because, well, we just did. Anyways, but notice that the way that we filled this out, something weird really happened. A dot B is equal to B dot A is equal to E, which means that A and B are inverses of each other, right?
Yeah.
Similarly, A dot C is equal to C dot A is equal to E, which means C and A are inverses of each other. And similarly, B dot C is equal to C dot B is equal to E, which means C and B are inverses of each other.
How does that work?
But that makes
It's not a very well-behaved operation. There isn't one and only one inverse. Some have multiple inverses. Notice that we had this exact same problem when we were trying to define modular multiplication.
Yeah.
And we said not everything has one and only one inverse. And you can't go around talking about the inverse arbitrarily. You need to be careful to make sure that there's only one inverse, and then we'll talk about the inverse. So here's a table showing that exact problem. This is a perfectly valid operation. It has an identity element, but you'll notice that the inverses are not behaving nicely, right? Okay. So now we're ready to start talking about groups. Let's read the definition and then come back to examples, rather than trying to prime you for it. And then, yeah, this will be fine. So let dot be an operation on a set G. So G is now just a set of numbers, well, of anything. Then G dot, that ordered pair together, just like you're used to SP, this is G dot, a set and an operation, is called a group provided that we have four properties met. 1, G is closed under dot. If I take two elements out of G and I dot them together, I still get something in G. It has to be closed. 2, has to be associative. Associative, that's right here. A dot B dot C has to be the same thing as A dot B dot C in order for it to be a group. 3, G has to have an identity element. And then finally, 4, for every element in G, for every small g and big G, there has to be some h in big G, such that h is the inverse of little g. In other words, every element has to have an inverse element in order for it to be a group. Every element has to have an inverse element, otherwise it's not a group.
It has to have an inverse element in the set, right?
In G, yes, in G.
Okay.
Every element in G has to have an inverse element in G, otherwise it's not a set, or otherwise it's not a group. Good? Alright, so let's go over some examples of groups. Groups. Addition on Z. That's a group. Or Z comma addition in the ordered pair. Probably would have been a better way to write that. Let's check. Is addition closed on the integers? When I take two integers, am I guaranteed to get out an integer?
Yeah.
Yes. What's next? Is there an identity element in Z for addition? What is it?
0.
0.
You forgot
Oh.
associative.
I forgot associative. Is addition associative on Z?
Yeah.
Yeah. And then finally, for every element in the integers, can I find an additive inverse?
Yeah.
Yeah. What's the additive inverse of 5?
Negative.
Negative 5.
But it's not oh, yes,
Z.
yes.
These are all the positive and negative numbers.
I was thinking that one.
What about the additive inverse of 0? It's
Negative
just 0.
Yeah.
0 added with 0 gives you back 0. 0 is the one and only number you can add to 0 such that you get 0. So nothing wrong with that. Does this one make sense?
Yep.
Alright, let's look at the next one. Modular addition on Zn. Remember what Zn is? That's good, because we just did a test on it, right? Okay, let's check this one. First off, is it closed? Yes, that's something we explicitly proved, but it makes perfect sense if you think about what this plus is. What does it mean to have A plus B? That is the same thing as A plus B mod n. And when I mod it by n, my remainder is definitely going to be less than n, right?
Yeah.
So we'll get an integer less than n. So, yep, it's closed. Is it associative? Yep, we just use the fact that regular addition is associative to prove that. I don't remember if we actually proved that one, we just stated it. We stated it for sure, I don't remember if we proved it. We might have. Let's see, what's next? Does it have an identity element? Yes, 0. 0 is always in Zn, right? Because n's a positive integer. So 0 is always and forever in there. And A modular addition 0 is the same thing as A plus 0 mod n is just A. Good?
Yeah.
Let's see. What are we missing? Does it have an inverse? Whew, that's a harder one. Does every element in there have an inverse?
No. No, it doesn't. Yeah.
Yes, it does. How would you calculate it? Let me show you the pattern so that you understand it. Give me an actual n to put here.
12.
12?
Oh.
He's going to make this real easy for me. Okay, give me any number you want now, and I'll find its inverse. 6? 6 is the inverse of 6. Give me another one.
How is 6 the inverse of 6?
What's 6 plus 6?
12.
Mod 12.
6, 12. Oh, it has. I forgot, okay.
What is the remainder of 12 when you divide by 12?
Oh, 0.
0.
Do 4.
What's your point?
4? 8.
How?
What's 4 plus 8?
12.
What's 12 mod 12? So you got 0. That's the identity element.
I know what
Oh,
yeah.
let me write this more explicit. Sorry, if we're losing it, I should be more clear. 6 plus 6 in Z12 is 0. 4 plus 8 is equal to 0.
Oh, an inverse is
And
equal
in
to
general,
0.
x plus n minus x is equal to 0.
What about 12?
12 is not in Z12. This is the numbers 0, 1, 2, 3, all the way up to 11.
What about
You have
11?
to pick two things out there. 11,
Oh,
1.
Okay, that makes sense.
But it doesn't work on modular arithmetic on times, right?
No, times we have a whole bunch of problems with.
Yeah.
We'll come back to that one at the very end. But was that all the properties for it? Yeah. Okay. So that one wasn't too bad. This is times on the positive rationals. Times on the positive rationals. Is that closed? Multiply two positive rationals together. You get a positive rational? Yeah. Is it associative? Yeah, we know multiplication is associative. We've been doing that since grade school. Does it have an identity element? Yeah, 1 is still the multiplicative identity. Does every element have an inverse? Yeah. What's the inverse of 3? 1/3. Yeah? No?
A equals 1, right?
Yeah, 3 times 1/3 is 1.
So it has to equal the identity element?
Yes. For it to be an inverse, it has to equal the identity. That's exactly right. That is exactly what our definition of an inverse is. B is an inverse of A, provided this is always the case. Alright? And then it sounds like you guys are a little bit foggy on the set of all permutations and composition.
Yeah.
So maybe that will be a useful example, and that will just confuse you more.
Yeah. It's not associative.
It is associative, it's not commutative.
Oh.
And we proved it was associative. Function composition is associative on the set of permutations. Okay. So now, let's see. Oh, next definition. Okay, so you notice so far all we gave it was associativity. We didn't give it commutativity. So if you make it commutative, then the group is now what's called an abelian group. So an abelian group is a group where the operation is also commutative. So this one happened to be an abelian group as well. This one's an abelian group as well. This one's an abelian group as well. This one was not. Function composition, you can't switch the order and not change how it works. Make sense? Okay. Now we're doing a proof. Every element in a group has a unique inverse. Okay, so it turns out that an operation being associative implies that it has a unique inverse. So we're going to prove that real quick. Well, we're going to prove that a group, every element in a group has a unique inverse, and a group has those 4 properties. So every element in a group has a unique inverse. Let's prove it. Let G and dots be a group, and let X be any element in G. Have we proved that X has one and only one inverse? First off, by definition of a group, X does have an inverse. We'll call it Y. By definition of a group, every element has an inverse. For every little g, there exists a little h such that h is the inverse of little g. So X has an inverse, we're going to call it Y. With me so far? We know that just because it's in a group. Now assume by way of contradiction that there exists Y prime, such that Y prime is also an identity element. This is the same thing as saying an identity element. And Y is different from Y prime. They're not the same value. Good?
Yeah.
Now we're just going to use good old associativity to prove this. Then Y is equal to Y dot the identity element, right? But then the identity element is the same thing as X dot Y prime. You with me there?
Yep.
Now, because of associativity, we can rewrite it this way. We can move our parentheses. That's what associativity lets us do. Now, Y dot X is the same thing as E. E dot Y prime is just Y prime. So we got Y is equal to Y prime. You follow the algebra there?
Yeah.
Yep. Is there a weird step? Think you got it? Think you could reproduce a proof like that? Because it's exactly the type of thing that would be on the test. Therefore, Y is unique. Good? Okay. So now, let n be a positive integer. We're going to define Zn star. So we already had Zn. What was Zn? Z sub n? It was the set of all the integers starting at 0, going all the way up to n minus 1, right?
Yeah.
So Z sub 10 was 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was Z sub 10, right?
Yeah.
So now we're going to define Z sub n star. It's going to be a subset of Z sub n. So z sub n star is equal to the set of all the elements in Zn such that their GCD with n is 1, or such that they're relatively prime with respect to n.
Will you re-say that?
It's probably easier to read it than have me say it. Z sub n star is equal to all the elements in Z sub n such that the GCD with that element and n is equal to 1. Or in other words, it's relatively prime with respect to n. So let's do an example to make sure you're getting it. Let's look at Z sub 14 star and look at everything in there. Now, first off, this is going to be a subset of Z14. What is Z14?
From 0 to 13. 0 to
All the numbers from 0 to 13, right?
Yeah.
Now, which of the numbers between 0 and 13 are relatively prime with 14? Or in other words, when you take their GCD with 14, you get 1.
7.
7 is no. What's the GCD of 7 and 14? 7, because 7 goes into 14.
Gotcha. Okay.
So let's start with 0. What's the GCD of 0 and 14?
0.
14.
How is
14 is a divisor of 0. Is there an integer that I can multiply 14 by to get 0? Yes, 0. So every positive integer is a divisor of 0. So 0 is not in there. Let's look at 1. What's the GCD of 14 and 1? 1. So that one is in there. Okay, so we got a 1. Wonderful. Is 2 in there?
No.
We'll have you go one at a time, starting with Peter. Peter, is 3 in here?
Yeah.
Yeah. Emma, is 4 in here?
No.
Laura, is 5 in here?
Yeah.
Yeah. Rhoda, is 6 in here?
No.
I mean, is 7 in here?
No.
I mean, is 8 in here?
No.
All right. Leah, is 9 in here?
No. Yes.
Stafford, is
How
10
is
in
9
here?
in there? 3.
Yes.
10? What's the GCD of 10 and 14?
2.
2. They're both even. No evens can be in there.
Wait,
All right.
9. 3 times 3 is 9.
3 times 3 is 9. What's the GCD of 14 and 9 though? Maybe you didn't know what we were doing. What is the greatest common divisor of 14 and 9?
Oh, so it has to be combo. Okay.
Yes, it has to be a common divisor, and it has to be the biggest of them.
Okay, go ahead.
All right. So, not 9, not 10. What about 11?
Yes.
Yes, 11's in there. What about 12?
No.
No.
Obviously, none of the evens can be.
Obviously, none of the evens. There we go. What about 13?
Yeah. Yes.
And then obviously, you guys were just reading my list of numbers here.
Yep.
I wasn't.
To get the next example. Okay, so there we go. That's Z14 star. That is all the numbers from 0 to 13 whose greatest common divisor with 14 is 1. Sounds like a mouthful, but it's a pretty simple concept, right? So if I had you calculate Z star of 52, you could do that, right?
With a calculator, I probably could.
With a calculator, you still only probably could. Okay. So now, let's look at this times table for a second now. This time it actually is a times table. And it's a times table on that set. And what I want you to notice is that every single number has a multiplicative inverse. So 1 has a multiplicative inverse, it's 1. 3 has a multiplicative inverse, it's 3 times 9 is 13. how a multiplication table works? So we're taking all the numbers in our set, and we're timesing them by all the numbers in our set using modular arithmetic multiplication, right?
Yeah.
So another way to think about it is, what's 1 times 1?
1.
Mod 14. It's still just 1.
Yeah.
Okay, let's look at another one. Let's look at 5 times 5.
Is 25 a mod?
Mod 14 is,
11.
how did you do that?
Does that work?
It's not that hard to do. How many times does 14 go into 25?
2.
What's 2 times 14?
1.
1. Okay.
I was just kidding.
So 14 goes into 25 once with a remainder of?
That is 9. Oh, 11.
11! There you go. Let's do one more. Come stand right here. I just need 2 numbers. Let's see, we'll do 9 and 5. What's 9 times 5?
45.
How many times does 14 go into 45?
4.
Does it?
No.
Okay. 3. What's 3 times 14?
32. 42.
42. So what is the remainder of 45 when you divide by 14?
3.
3. So 9 and 5 gives us 3.
Okay.
That's how this table was populated. Now you know how to do it, and you can make your own table, right? Wonderful. Now, back to what I said before, I want you to notice that every number has a multiplicative inverse. Right?
Yeah.
Now we're noticing it for the special case, but this is very much hinting at the fact, whoa, can I take this group and this operation, not this group, can I take this set and this operation and end up with a group? Will it have these 4 properties? It being closed, that one seems kind of obvious, but turns out that's the hardest to prove. Is associative. We already know that this is associative. We've already proven that. Does it have an identity element? Yeah, 1's always going to be in there, right? 1 is always relatively prime with respect to any n. Does every element have an inverse? That one might be kind of harder to think about, but this table kind of hints at maybe it does. Because this was just a special case. So now the next thing we're going to do is we're going to prove that this with this operation is a group. And that's what's over on the other board. Before I move the camera, any questions about what we have written up here?
Okay, wait. If n is 1, then does it have an identity element?
1 is the identity element. Does it have an inverse? Yes, it's 1. 1 is the multiplicative inverse of 1. That's why dividing by 1 and multiplying by 1 are the same thing.
Like if 1 is n,
But it can't be
is
12.
the set just 0?
Yeah. So the thing's only
Say
0.
that again.
If n in that is 1, is the set just 0?
So it doesn't have
So
an
Never mind.
Oh, I see what you're saying. You're saying, what if n is 1?
Yeah.
Then we only have... Oh, is that what you were saying?
Yeah.
Oh, I thought you were saying for 1 in the set. Sorry. Good question. So, if n is just 1, then Zn is the set only containing 0, and this set is empty. So you are right. We need it to have not any positive integer, but a positive integer greater than 1. That is a good point. So, let me double check the book to see if I wrote that wrong. Or if we're missing something obvious. Let n be a positive integer, then z star n is a group. Yeah. That should say greater than 2. Or greater than 1. So I think that's a mistake in the book. I think that n has to be greater than 1. All right, now I'm going to move the camera before we continue. That's a bad sign. Means you're really bored.
That is not true.
No, not
It's just
necessarily.
in the same area.
Why won't it zoom?
Kind of weird.
Oh well, not gonna fight anymore. Okay, so let's go over our last proof of the day. Proving that z star n is a group. So first off, let n be any positive integer. Now I should say any positive integer greater than 1, I think. Then z star n with modular multiplication is a group. So first off, let n be a positive integer and let a and b be elements in z sub n. So we're assuming z sub n is not empty because it has to have the identity element 1. Okay, so since a is in z sub n, remember what zn star is. What is it? It's all the numbers that are relatively prime with n, right? Let me explain what we're doing first, maybe. So we've got n in there, we've got 2 elements. First thing I'm trying to do is show that it's closed. First property of the group, it's closed. So I need to grab 2 elements out of there, and I need to show that this times this is also in there. Does that make sense? We already know that this times this is in Zn. The question is it in Zn star still? That's the question. So it's not quite so trivial. Make sense? Okay, so we have A is in Zn, but that means it is relatively prime with n.
Yeah.
So that means that its GCD with n is 1. Now, if the GCD between 2 numbers is 1, then there exist 2 integers, x and y, such that ax plus ny is equal to 1. I told you that was the second most important theorem in all of number theory, was going from this to this, right?
Yeah.
Yeah.
Similarly, since b is in Zn, we know that GCD of b and n is also 1, which means that there's 2 integers, w and z, such that this is true. Good? Now we're going to rewrite 1. Then 1 is equal to 1 times 1 is equal to 1 times 1 is equal to just distributing. Now, notice that I'm going to have one term that has a and b in it, and then all my other terms are going to have an n in it. So here's my one term that had a and b in it, and then here's n factored out of all my terms my other 3 terms that had n in it. All I'm showing is that, look, 1 is equal to a times b times an integer plus n times an integer. You with me?
Yeah.
So if 1 is equal to that number times an integer plus that number times an integer, then the GCD of these 2 numbers is 1. You follow that logic? Going backwards from what we did up here. Going from here to here, but we can also go from here to here. So I just really went from this to this.
How can you
I
do
went
that?
from this equal to 1 to this.
I'm confused how you can. Okay. I think I see.
Cut up?
Yeah.
Anyone still need to just look at it, or are we ready to continue?
I think we're good.
Okay. So now, since the greatest common divisor of a times b and n is 1, then the greatest common divisor of a times b mod n and n is still just going to be 1. So a times b with modular arithmetic is still going to be relatively prime with respect to n. Does that make sense? Pretty straightforward? Anything weird? I think going from this to this is an exercise that they're going to have you do, or that you've already done. I can't remember which. But if this is relative, if these two are relatively prime, then adding or subtracting multiples of n from this isn't going to change that fact. Okay. Right? So it's similar thinking to when we're doing mod n, adding multiples of n doesn't really change the number, subtracting multiples of n doesn't really change the number. Same thinking. Because when we talk about its GCD being 1, we're going to talk about the remainder when we divide by n. So we're going to take away multiples of n anyways. Remainder's going to be the same. Okay. So that is for sure in there now, because its GCD with this is going to be 1. Therefore, multiplication is closed on this set. If you pick two elements out of here and you multiply them together, you'll get something else in here. But now we're saying it more generally for this set. Anything weird? Okay, so that's the first property. Now the next property, showing that it's associative. Well, observe that that is associative. We already proved that one, right? And it's just using the fact that multiplication itself is associative. Okay? The next one was showing it has an identity on it. Well, observe that the GCD of 1 and n is always equal to 1 for any positive integer n. Therefore, 1 is always in Zn. Oh, and then that just says that 1's in there. I also argue that it is an identity element. So we already knew that this multiplication was commutative. That's what we already knew for modular arithmetic. So I know that this is commutative, so I already know that those two are the same thing. But then what is this? That is the same thing as this, is the same thing as this, is the same thing as this. So a times 1 is 1 times a is a.
Right.
Good?
Yeah.
So it's an identity element. Now, last thing we need to prove, that there's an inverse. Okay. Let A inverse be the inverse of A. Now, we already showed that if a number is relatively prime with respect to n, it has an inverse, a multiplicative inverse. We already proved that, right? All I need to do now is show that its inverse is inside this set. So we already know that everything in this set has an inverse. We should know that the inverse is also in the set. That's all we need to verify now.
Okay.
Right? Anything weird about what I'm saying? Ready to just continue? Okay. So let A inverse be the inverse of A, and it remains to show that A inverse is in Zn star. Well, since A inverse has an inverse, namely A, then it is relatively prime to n, and so A inverse is in there, because that's the set of all things relatively prime with respect to n.
Can you explain that?
We showed
Literally
that.
just said the same thing.
I know. That's because I'm just using something that we already proved. We already proved that a number has a multiplicative inverse in Zn. In Zn. What numbers, let's say that Zn will make it 10. What numbers have a multiplicative inverse?
All.
Relatively prime term.
Not all of them. Multiplicative inverse.
Oh.
1, 3, 7. Those are the ones with the multiplicative inverse, right? We proved that if a number has a multiplicative inverse in Z10, if and only if it's relatively prime with respect to with n. In this case, 10. We did that proof. You don't remember that? How do we calculate the multiplicative inverse?
Is it mine?
Euclid. Extended Euclid. Do you remember that?
Yeah.
You're doing it with all the numbers, all the numbers, all the numbers, and you get it equals 1. And then once it equals 1, you work backward, so you get 1 equals some number times x plus some number times y. And that's how you get your multiplicative inverse. So you can get a multiplicative inverse if and only if you can rewrite it so that its remainder is 1. So that's GCD is 1, is what I meant to say.
Yeah.
When you divide by n. So that's how we know that 3 has a multiplicative inverse.
On that set, would it 9 also be in
Yeah,
there?
that's what I'm wondering.
Oh, yes, 9, thank you.
That's
Because
what-
9 is going to be its own. Okay, yeah, good catch. So 1 is its own multiplicative inverse, 9 is its own multiplicative inverse, and 3 is 7, and 7 is 3's. Right?
Yeah.
So you're in this set if and only if, or you have an inverse if and only if you're relatively prime with 10. Right? That makes sense? So, since this, by definition, is all the numbers that are relatively prime with n, they all have an inverse. So everything in here has an inverse. Does that make sense? Because they're relatively prime with 10.
Yeah.
Then, looking at its inverse, since its inverse has an inverse, namely the initial number, it has to be relatively prime with n. So it's in there.
Okay.
So the inverse is also in there. It's using the same piece of logic, except for one way than the other. Because this is an if and only if. So that's why it feels like I'm basically saying the same things twice, because I'm referencing the same if and only if theorem twice. I know that every element has an inverse, because everything in here is relatively prime with respect to n, and therefore has a multiplicative inverse, A inverse. And then I know A inverse has multiplicative inverse, namely A, the element we started with. Therefore, A inverse is also in there. That make sense? Okay. So then every element has an inverse element, and therefore it's a group. And that's it.
This only works with the modular arithmetic multiplication, though, right? Or does it work with any?
Well, this proof is just proving that that special set with that special operation is a group. Now, everything you prove about groups in general is also true about this special case. So what did we prove about groups over here? We proved that a group has a unique inverse element. We know it has one. We proved it's a unique inverse element. Now we know that this set has a unique inverse element since it's a group. We didn't need to manually check one's the only inverse that it has. We didn't need to check every other thing and make sure it's not inverse. We already have a generic proof showing that for any group, there's only one inverse.
Isn't that an identity element?
Identity element. Thank you. I said inverse, I meant identity this whole time. What other proofs did we do? Every element in a group has a unique inverse. So we already knew that A had a unique inverse because we specially proved that last time. But so that doesn't give us any more. We didn't do a lot of proofs with groups, but you did logic. And you probably remember that there were like 10 theorems that we did for groups. And we just went through proving them one at a time. I don't remember what they all were, but they were just a bunch of proofs about groups in general. Now we proved that this thing is a group. Therefore, all those theorems that we proved about groups in general are also true about this thing. They're also true about this thing. They're also true about this. They're also true about this. They're also true about this. Any group, those properties hold for. So this is a special group. Anything we prove about groups in general also applies to this.
Okay.
That make sense? And that's what you're trying to do in abstract algebra, is work with abstract algebraic structures. And so a group gives us a way of talking about a bunch of sets and a bunch of different operations at the same time, proving a bunch of things about them. Same way that when you prove something about the evens, you prove it for all even numbers. You're not just proving it for 12, even though it happens to be true for 12. So we're doing similar things now with sets and operations. Pretty cool at how high of a level we're talking. And all the different things that can fall into this category of things that we're talking about. Everything that falls into the category of groups. It's quite a variety of structures. Any other questions? Okay. Go on break, and then the rest of the class for homework, questions, whatever.